Woo! All right, so we are doing our last skill notes for the semester. Normally we do it before the Unit 5 test. We decided not to in this case, so that's why we are here at the moment. We normally also lead in with an investigation, but we decided not to do that this year. And so I'm just going to tell you the 3 different ways to tell if 2 functions are inverses of each other. Okay, so if we are inverses, think about addition and subtraction. They undo each other's operations, right? So if I were to numerically test, well, the input generates an output from the function. Generates an output from the function. Okay, so we have some x value that generates some corresponding y value. Then the output becomes the input for the inverse and generates an output that is the original input. So many words. So we have some input, right? And we put that into the function, the given function, and that generates an output. We then use that output as the inverse x value, the inverse input, and that will generate an output that is the original input. What the heck does that look like, Patterson? It looks like this. If I have f of x and it equals y, and then I have f inverse of y, okay, so we have an input that generates an output. That becomes the input for the inverse. Notice I have a -1 exponent because that's how I note that it is an inverse, and its output will be the original input. So numerically, how do we test? We substitute in values to see if it works in that circular fashion. Now, graphically is so nice. If you have 2 functions that are inverses, they are symmetric, so they are mirror images. They are symmetric across the line y equals x. They are symmetric across the line y equals x. Reflective, mirror images. What does that mean? That means that their domain and range elements switch. Think back to geometry. Yep. If you have functions or pictures that are symmetric across y equals x, their x and y values switch. And then algebraically, this is where composition comes into play. So if we are given 2 functions and we're asked to prove algebraically if they are inverses, well, f of f inverse will always compose to x, as is f inverse of x will always compose to x. So if you compose the 2, they give you a result of x, then you know that you have inverse functions. 3 different ways, ladies and gentlemen. Let's play with them. Here we go. Example number 16. Determine or prove whether the functions are inverses or not. Okay, so looking at the first one, we're given f of x and g of x. So I'm going to first compose, because it asks algebraically, for f of g of x. That means I'm going to take f and I'm going to substitute in g of x, which is x plus 4 over 3. Just taking this and substituting it in. Okay, well, f of x is 3x minus 4. So there's only one x value I need to substitute in for. We have 3 times x plus 4 over 3 minus 4. And then we're going to simplify and see if it composes to x. When we multiply, the 3's are going to reduce, and we'll end up with x plus 4 minus 4, which is, yep, you guessed it, x. So we say yes, they are inverses. Now the nice thing is, if one of them works, so in this case, f of g of x worked, guess what? G of f of x will work as well. So you're more than welcome to check both composition directions, just in case you think your algebra is incorrect. But if one of them works, the other one should as well. Okay, let's stick with the algebraic. Let's look at B. So g of x and h of x, we need to compose to see if they compose to x. Again, order doesn't matter, so let's switch things up. I'm going to compose h of g of x. Okay, so that means we're going to take g of x, which is 2x minus 3, and we're going to substitute into h of x. There's only one input. Excellent. So we have negative 2, input the quantity of 2x minus 3, and then we have plus 3 on the outside. Okay, so distribute the negative 2 with me. We get negative 4x plus 6 plus 3. Oh, I don't see anything canceling out. Now, when we compose them, we get this beautiful linear function. But ladies and gentlemen, this is not x. If one direction doesn't work, guess what? Neither will the other one. So we say no, they are not inverses. Dun, dun, dun. All right, so that's algebraically. Well, what about graphically? Let's look at a method number 2. Now, we already know through method 1 that example A, they are inverses. But let's test it graphically. Who knows? Maybe our algebra was wrong. So I'm going to rewrite down here just because I want to expand my screen a little bit. That way we can see. Okay. Right away, g of x is not in linear form that's friendly for graphing, in my opinion. So I'm just going to rewrite this as 1/3 x plus 4/3. Now it's in slope-intercept form, and I'm going to color code so we can see which is which. Now, y equals x, ladies and gentlemen. That goes through your origin. I am going to sketch it in here. Oh, not with that. Certainly not with that. There we go. So that we can see where that line lies, and we can see a little bit better if our graphs are symmetrical. Now, for that for that blue function, our y-intercept is at -4. And we're going to go up 3 and over 1, up 3 and over 1, since that's our slope. Okay, go ahead and grab your rulers or your straight edge of some sort so that we can draw this line. And I'm going to go ahead and write next to it that this is f of x. Now we're testing, is g of x an inverse? Well, 4/3 is 1 1/3, so I'm going to carefully graph that. And then I'm going to go up 1 and over 1, 2, 3, doing my best to uphold that 1/3 on the graph. Okay, grabbing my straight edge again. Sorry if you can hear the wind. It is blowing down my house. And then I'm going to connect the points, noting that this is g of x on my graph. Okay, so it looks as if they are symmetrical across y equals x, but let's test, yeah? Let's test a point. Okay, well, we have a point here. That point happens to be 0, -4. If they are true inverses, then we would have a point at, we would have a point at -4, 0, because their x and y values switch. So, yes, they are inverses. Nice. Okay, so let's test this one. Yes, again, we already tested it algebraically, but we need to practice with the graphing method. So let me write this out. Okay, again, I'm going to have one be blue and one be orange so that we can differentiate between the two. And I'm going to sketch in my y equals x line of symmetry. It's not an axis. It is a line of symmetry, though. Okay, so for the blue, for g of x, I'm going to go down to -3, and then I'm going to go up 2 and over 1, up 2 and over 1, grabbing my straight edge, because Lord knows my straight lines need some improvement. There we go. And I'm going to label it g of x. Even though it is color-coded, labeling helps those who are looking at your work, looking at your graph, to truly understand what they're looking at. Okay, for h of x, I'm going to go up 1, 2, 3. I'm going to go down 2 and over 1, down 2 and over 1. Grabbing my straight edge yet again. Trying to line it up nicely. This is where my OCD tendencies don't help me, but I can get it closer. Just draw the line. Okay, so there is h of x. Well, we can easily see, looking at the graph, that they are not symmetrical across y equals x, but let's say we can't see it. Maybe we have a hard time with that. First off, that's okay. We can't always identify symmetry just by looking at something. So that's where the line test comes into, or the point test, pardon me, comes into play. I have a point, and you can pick any point, at 0, -3 for g of x. If these are inverses, then there should be a point at -3, 0, and there is not. So we can tell, since their x and y values don't switch, nope, they are not inverses. Nice. Okay, so two different ways to test if given functions are inverses, either algebraically or graphically. Well done. So let's find inverses and determine if they are functions. Remember, in a function, the x values do not repeat. Okay, so we're asked to find the inverse and determine if it's a function. For example A, we're given a relation. Now, if you need to write this down as a reminder, a relation is a set of points. Looking at our x values, we have -1, -3, -1, and 0. Well, this relation is not a function, but we weren't asked that. We were asked to find the inverse. So let's label this f of x. To find the inverse, remember, we have to have that -1 exponent. That means f inverse of x. Well, if inverse functions are reflective across y equals x, guess what? All we're going to do is switch their x and y values, because that is a property of inverses. So -2, -1, -3, -2. Nope, just kidding. Didn't switch that one. -2, -3. There we go. -4, -1, and 6, 0. That is the inverse. Now, is it a function? Well, we've got -2, -2. It's not a function because the x values repeat. So we're going to put no. Not a function. So again, if you're given a relation, a set of points, in order to find the inverse, you simply switch the x and y values. Okay, well, what if you're not given a relation? What if you're given an equation? Haha, same thing. We're going to switch the x and y values. Don't forget, f of x is interchangeable for y. So the first thing that I'm going to do is I'm going to write f of x as y. It's just a little more visually pleasing. And then I'm going to switch x and y. So switching the x and the y, but let's be honest, ladies and gentlemen, we never have x as the output. So step 1, switch the x and y's. Step 2, solve for y. So I'm going to subtract 2 to both sides. We get 1/2 y is equal to x minus 2. And then I'm going to multiply everything by 2 so I can get rid of that fraction. Don't forget to distribute the 2. We end up with y is equal to 2x minus 4. But be careful. F of x and y, these do not represent the same function. Therefore, I'm going to put f inverse of x is equal to 2x minus 4. You have to write it as the -1 exponent. You could, if you wanted to, put y inverse. They're interchangeable. Okay, now what did we find? Hey, we found a linear function, which, yes, I used the word function because it is a function. It is a line that does not have x values that repeat. So yes, it is a function. Okay, let's take a look at example C. Ooh, beautiful little quadratic we have here. We're asked to find the inverse. So I'm going to write y equals x plus 2 quantity squared minus 3. And then following my steps, I know that in order to find the inverse, I need to switch the x and y. So x is equal to y plus 2 squared minus 3. And then I'm going to go ahead and solve for y. So let's add 3 to both sides. Y plus 2 quantity squared is equal to x plus 3. Now, we're solving for y, so I'm going to have to take the square root of both sides. To get rid of that square, we get y plus 2 is equal to, ladies and gentlemen, the big elephant in the room, we need to have the plus and minus. Plus and minus because we're solving. We chose to take the square root. And then our grand finale, y inverse or f inverse. You don't need both of these. I'm just putting both of them so that you can see they mean the same thing, is equal to negative 2 plus and minus the square root of x plus 3. You can most certainly write the negative 2 in the back, but be careful because when we have a number or anything in the back of the square root, make sure you can tell it's literally outside of that radical. Okay, think about what this is graphically, right? It is the positive and the negative of our square root. The positive and the negative, is this a function? No. And think about what a parabola looks like. Its range values repeat, right? Its range values repeat. So for inverses, if the domain and range values switch, it follows that, yep, this is not going to be a function. Okay, so if the range repeats in the original function, then the domain will repeat in the inverse. So no, it's not a function. Wah, wah. Okay, let's take a look at D. It is a cube root, and yep, you guessed it, we need to switch the x and the y. We were asked to find the inverse function. We were not asked to verify. We were asked to find the inverse function, okay? Be careful, you guys. If you're asked to verify, that's what we did on the first page. Now we're finding it algebraically. So let's cube both sides, please. 2y minus 5 is equal to x cubed. We cubed both sides so that we could get rid of that cube root. I'm then going to add 5, so 2y is equal to x cubed plus 5, and divide by 2. Y inverse, don't forget the inverse symbol, is equal to 1/2, because I divided by 2, times x cubed. I don't know why I'm using a parenthesis. Plus 5/2. If you're so inclined, you can put it as x cubed plus 5 all over 2. That's the same thing. And as we know from all of our functions this semester, there were so many, this is a cubic. A cubic is a function. Yes, it is a function. All right, so we verified. Now we found the inverses, and now we're gonna sketch the graph of the inverse of each relation. Think about what we've been talking about. Their x and y values switch. So let's identify points on this given relation. We could say that there's approximately 1 point at 2, 3, negative 3, comma 0. And then we highlighted another point at 0, 2. And we highlighted another point at 3, 0. So if we were to graph its inverse the x and y values would switch. So the inverse would have a point at 0, -3, and 2, 0, and 0, 3. It's the theme we've been talking about, you guys. It's all about the x and y values switching, the domain and the range elements trading off. So let's plot these points. 0, -3, 2, 0, and 0, 3. This point was at the curve, so we're going to extend out to these points. And if you're not sure, go ahead and sketch in y equals x to see if that looks like it would reflect. It certainly does. Nice. Okay, so let's try that again on B. We're given a linear function. I'm going to identify a couple of points. Let's say, oh my, not that. Come on, blue. There we go. Let's identify this point and this point and this point. Okay, so the first one is 0, 4, and then 2, 2, and then 4, 0. If I'm going to graph its inverse, that means I'll have a point at 4, 0, 2, 2, and 0, 4. Go ahead and graph those with me. So 4, that's strange. 2, hey, that tricky linear function. It is reflective across y equals x. Ladies and gentlemen, this particular function, its inverse is itself. That's kind of cool. Anybody know why? Curious to hear your thoughts. All right, pause this video, please. How can you determine if an inverse is a function? I'd like you to, in your own words, state, well, algebraically, numerically, graphically, domain and range elements, all of that should be written down. Please pause and then come back and join me. Hopefully you guys did pause and write down in your own words some reminders. We need to be able to apply the concept of inverses to real life situations. It's all about input, output, action, reaction, and then reversing. So if we look at example 19, we're given this graph. Okay, so the function f of x represents the number of songs that Elton has learned to play on the piano after x months. So right away, I'm going to label my graph number of months for the x-axis. Okay, and then f of x represents the number of songs that he's learned to play. So f of x is the number of songs, we'll say. Okay, use the given to answer the questions. Well, what is the value of f inverse of 4? Right away, I see that inverse symbol, and I know that I'm gonna work backwards. I'm not gonna look at this as my input for x. We're working backwards. That means I'm looking at 4 on the y-axis, and I'm seeing that it corresponds to 1. Y inverse, working backwards. So f inverse of 4 is equal to 1. What does that mean? Well, input, output, it's always if this, then that. Here, we're working backwards, and it's still if this, then that. So what does this mean? This means that Elton learned 4 songs, or if, let's back up, sorry, you're having to erase too. If Elton learns 4 songs, then it has been 1 month. The reason I know that it's the if-then relationship is because your x-axis is always the independent. Think back to graphs that you've seen where x-axis is always time. Yep, because time is independent. Nothing affects it. It has an effect. As you get older, things happen, right? Time marches on. So if we were to reverse and talk about the inverse, then our y-axis becomes the independent. We have to understand that switch. Okay, so let's do, I believe we have just one more, you guys. Use the given information to answer the questions. Same idea, okay? X is going to be our Celsius temperature of an object. So I'm going to highlight, since I don't have a graph, that way it'll pull my attention. And then F of X is the associated Fahrenheit temperature. Okay, so determine the value of F inverse of 10. That means F inverse, the Y is the independent. We just talked about that with the graph, right? So I'm going to look at 10 and what, ooh, not with that. I'm going to look at F of X because that is the Y. And what does that correspond to? That corresponds to negative 12 and 2/9. So explain what the value from part A means in terms of the context. Well, it means if the temperature is 10 degrees Fahrenheit, then it will be, because this is causing a reaction, right? If it's 10 degrees Fahrenheit, then it will be negative 12 and 2/9 degrees Celsius. All about moving back and forth, if, then, input, output, independent, dependent. Hopefully that makes sense, ladies and gents. You did it, semester 1.